All right, so let's talk about how to use method of initial rates to determine the rate law for a chemical reaction. So we have set up 4 different experiments. Each experiment has determined its initial concentrations for each of the 3 reactants. And then we have data where we have measured the initial rate, presumably of products. So as we look at each of the experiments here, it looks like we're holding a lot of things constant. And the idea is we're going to choose 2 experiments where 2 reactants are held constant and only one of them is changed. So we can see the impact of changing that one reactant. So if we look at our first experiment and let's compare it to the second experiment, we have kept the iodide the same, we've kept the hydrogen ion the same, and all we've done is change the hydrogen peroxide. So any differences that we see in rate can be attributed to the hydrogen peroxide. So if we look at what we've done here, we have doubled the hydrogen peroxide, so we did this times 2. And so we're looking to see how the rate change compares to our reactant change. And so essentially, our rate change should be times 2 to some power, 2 to the x. And our job is to figure out what the x is. Whatever that exponent is gives us the order of the reaction for that reactant. So if I multiplied my reactants times 2, and it looks like I've multiplied my reaction rate times 2, that means the x value is 1. And that means that this is first order with respect to hydrogen peroxide, because the initial rate was proportional to the change in concentration for that set of experiments. So let's use that same idea, but we want to look at the other reactants to see what we get. So again, we're going to look at experiment 1, but this time let's compare it to experiment 3. So here we're keeping the hydrogen peroxide the same, we're doubling the iodide, and we're keeping the hydrogen ion the same. So any changes in rate can be attributed to the change in iodide concentration. So again, it looks like we multiplied that concentration times 2. You don't have to, but sometimes it's a little easier to see the doubling. But we did multiply that one times 2. So that means for the rate, we're looking at that to be times 2 to some exponent. And we want to figure out what that exponent is. And again, it looks like the rate has doubled when our iodide has doubled. So the x value for this one is also 1. And so we would say this is first order with respect to the iodide ion, because doubling iodide while keeping everything else the same, doubled the rate, that's proportional. That means the exponent in the rate law will be a 1. So we've got one more reactant to take a look at. So we want to look at 2 experiments that isolate hydrogen ion, because we haven't looked at that yet. So if we see experiment 1 and we compare it to experiment 4, the hydrogen peroxide's the same, the iodide's the same, and all we've done is change the hydrogen ion. So again, it looks like we did a times 2 here. And if we look at the rates, it looks like we say, oh, the rate didn't do anything. But it's really times 2 to some exponent, and our job is to figure out what the exponent is. So if we've really multiplied this by 1, we want to know what exponent would we have for 2 that allows the result to be 1. And so the x in this case is 0. So what we're finding here is that the hydrogen ion order is 0. That means changing the hydrogen ion concentration has no effect on rate, and we would say that it is 0 order. So the way we would write the rate law with this kind of data, we would say rate is equal to K, which is the rate constant, times hydrogen peroxide to the first power, times iodide concentration to the first power. And you could put hydrogen ion to the 0 power, but when it's 0, we tend just to leave it off. And so this would be the rate law based on this data for method of initial rates. So let's try this one again. We've got a different set of data here. We're asking a very similar question. We have a chemical reaction, ammonium plus nitrite ion is going to give us nitrogen and water. And we've set up 3 different experiments here where we're showing our initial concentrations of each reactant, and we measured an initial rate for that setup. So we want to do kind of the same thing. We want to look at 2 different experiments that isolate a particular element. So if I look at the first and the second experiment, the nitrite stayed the same, but I see my ammonium is different. So any differences in my rate can be attributed to the differences in ammonium. So it looks like I essentially kind of cut in half my ammonium, and it looks like I cut in half my rate. So that is a proportional relationship, which means my exponent would be a 1. We'd be first order for ammonium. And then I want to look at nitrite. So experiment 2 and 3. Ammonium stays the same, and it looks like I've multiplied my nitrite by 1.5. And I've also seen my rate go up by 1.5. That is proportional. So that means my nitrite is first order. So if I were to write a rate law for this, it would be rate is the rate constant, lowercase k, times ammonium to the first power, times nitrite to the first power. So it would be first order with respect to each of the reactants. We could say it's second order overall. And this would be the rate law that's consistent with our experimental data. So the next part asks to determine the rate constant with units. Like they actually want you to get a number value for K. We want to figure out what that is. So the cool thing about this is you have lots of data to use. The rate law that we came up with works in every experiment. Every experiment follows the rate law. So we just need to use one whole line of data to plug into our rate law. And when we do that, we have a rate, we have concentrations for each of our reactants, and K is our only unknown. So we plug in one complete line of data and then solve for K. So if we do that for this one, and again, it doesn't matter which line you use, any one line will work. So if you plug in data for that, you should get K is 3 times 10 to the negative 4th. K values can be a wide range of numbers. They can be really small and they can be really big. So kind of anything goes. Now the units can change, which is a little weird for a constant, but the units for the rate constant will change depending on the overall order of the reaction. So basically the rate constant units need to be whatever they need to be so that the units on the left side of the equal sign equal the units on the right side of the equal sign. So rate is going to be molarity per second. So that's capital M over S. Every time you have a bracket, that represents molarity. And so K needs to be whatever it takes to make this expression on the right equivalent in units to molar per second. So the units for K in this case would be essentially 1 over molar seconds, where molar and seconds are multiplied and on the bottom of the fraction. We'll play around more with that as we practice.